Good day, viewers. Welcome to our today's class. We are still on thermodynamic relations. The question above says the equation of states in the given range of pressure and temperature is given by V is equal to RT all over P minus C all over T cube. Where C is constant, we are asked to derive an expression for change of enthalpy and entropy for this substance during an isothermal process. So, in order to solve this question, we are going to be using our knowledge of the generalized form of change in enthalpy. So, the generalized form of change in enthalpy, which has been proven from our previous lectures, is nothing but the H equal to minus T into the partial derivative of V over the partial derivative of T, keeping P constant, dP. So this is what we have. So from the question, we said during an isothermal process, the question says during an isothermal process, we should derive an expression for the change of enthalpy and entropy. So during an isothermal process implies that the T will be equal to 0. If the T is equal to 0, we are going to put the T equals to 0 in this equation. So we are going to be having the H. Since we are keeping T to be constant, we are going to have the H keeping T constant to be equal to 0. That is, by putting the T equals to 0, automatically we have 0 here plus the bracket of V minus 2, the partial derivation of V all over the partial derivation of T, keeping P constant, constant because we let the T to be equal to 0. So next, we are going to be of state. We know that V is equal to RT all over P minus C all over T cube. So we said V is equals to RT all over P minus C all over T cube. This was given to us as our equation of state. So if we differentiate this equation with respect to T, we are going to differentiate this equation with respect to T. If we differentiate this equation with respect to T, we are going to have the partial derivation of V with respect to the partial derivation of T, keeping P constant, to be equal to R all over P plus 3 all over T to the power of 4. This is what we are going to be having. Now, we are going to substitute the value of this, that is the partial derivation of V all over the partial derivation of T, keeping P constant, for this in this equation. So if we do that, we are going to have the H plus 3 all over, where we differentiate this equation, all over T to the power of 4, close bracket, keeping the P constant, Next, we are going to be integrating this equation. We are going to be integrating this equation from 1 to 2. So if we integrate this equation, we are going to have the integral of 1 to 2 of the H will be equal to the integral from 1 to 2 of the bracket of V minus RT. What we are going to be doing is that we are going to be multiplying through this bracket by T. We will be left with RT all over P plus, this is going to be plus 3C all over T to the power of 3. Close the bracket. Close the bracket. We have the is the bracket of V minus RT all over P. We have minus T multiplying this. Where minus T multiply this, we are going to have minus T 3C all over T to the power of 4. And T which is here, we go with 1t here, we'll be left with t to the power of 3. So we have minus here 3c all over t to the power of 3. So this equation will be nothing of the integral from 1 to 2, integral of 1 to 2, change in h, which is have the integral of 1 to 2, the h, from 1 to 2 the h will be equals to the integral from 1 to 2 of the bracket of v. Now, we know that v, which has been given from the question, which is our equation of state, is equals to RT all over P minus C all over T cubed. So we can substitute the value of V for V in the above equation. If we do that, we are going to have RT all over P minus C all over T cubed. This is what we are going to have. Then we have our equation, which is minus RT all over P minus 3C all over T to the power of 3, close the bracket, dP. So this is what we have, close the bracket, we know that the integral for 1 to 2, from 1 to 2 of the h is nothing but h2 minus h1. So the integral from 1 to 2 is nothing but h2 minus h1, and from here we can now have the integral from 1 to 2 into the bracket of, we are having RT over P minus RT over P here. It means that RT over P minus RT over P can cancel out, which is equals to 0. We are having minus C all over T to the power of 3 minus 3C all over T to the power of 3. If we simplify this, we are going to be left with minus 4C all over T to the power of 3. If we do that, we are going to be having minus 4C all over T to the power of 3 dP. So this is what we are going to be left with. So it implies that if we do this, we are going to have H2 minus H1 to be equal to minus 4C all over T to the power of 3 into P2 minus P1. So this is what we are going to be left with. So this is what we have. How do we arrive at this place? Minus 4C all over T to the power of 3. We go out of this integral sign. If we do that, which is what we are doing is this. We are taking minus 4C all over T to the power of 3 out of this integral sign. And if we integrate from 1 to 2 dP, we are going to be left with P2 minus P1. It implies that this equation has been reduced to this. Now this can be referred to as an expression for change in enthalpy during an isothermal process, whereby we know that our equation of state V is equals to RT all over P minus C all over T cubed. So this is our equation for enthalpy. So next, what we are going to be doing is that we are going to be deriving an expression for entropy, still doing an isothermal process. So this is for enthalpy. Now we are going to be deriving an equation for entropy. Now, in order to derive an equation or an expression rather for change of entropy during an isothermal process, in order to do this, we are going to be using the generalized form for finding entropy. And we have proven this from our previous video. We know that the generalized form for finding entropy, that is the S, is equal to Cp dt all over T minus the bracket of the partial derivative of V all over the partial derivative of T, keeping P constant, dP. P. From our previous videos, we have derived this as a general equation for finding entropy. So next, we are told from this question that we should find the entropy for a substance during an isothermal process. So to do this, we are going to let the T to be equal to 0 since there is no change of heat. If we do that, this equation will be reduced to the S is equal to 0. This is what we have, all over T minus the partial derivative of V all over the partial derivative of T, keeping P constant, the P. So what we have just done, we have just let the S, we have just let the T, which is our change in temperature, to be equal to 0. This implies that this equation will become the S, since we are keeping T constant, is going to be the S keeping T constant to be equal to 0 minus the partial derivative of V, that is, we can say minus the partial derivative of V all over the partial derivative of T, keeping P constant, the P. Now we said the T is equal to 0. It implies that we can indicate that T is okay. So this is what we have. From here, we know that this equation is automatically 0. So what we have left, we are keeping T constant. So next, we know that, or we have proven rather, that we know that V is equal to RT all over P minus C all over TQ. Now, similar to what we did when we were looking for, when we were deriving an expression for enthalpy, we differentiated this equation of state. So again here, we are going to be differentiating this equation of state with respect to T. If we differentiate this equation of state with respect to T, we'll be having the V all over the T, keeping P constant, to be equal to R all over P plus 3C all over T to the power of 4. This is what we have when we differentiate our equation of state with respect to T. Now we can see that the partial derivative of V over the partial derivative of T, keeping P constant, is equals to this, and we are also having the same thing here. So we can substitute this value for this in this equation. If we do that, we are going to be having the S, close the bracket, keeping T constant. As we know, we have made T to be equals to 0. So from this equation, we are going to be multiplying this bracket through by minus. If we multiply this bracket through by the negative sign, we are going to have this equation to become nothing but the S of T, which will be equal to, we are going to have minus R all over P. This is of course into the bracket of P of minus rather 3C all over T to the power of 4. This is what we have, the P. This is what we have. Mind you, we have T, which is temperature constant. So next we are going to be integrating this equation from 1 to 2, just like how we did with our previous equation, just like how we did with our previous equation for change in enthalpy. So now we are going to be integrating from 1 to 2, that is the S. The integral from 1 to 2, the S, will be equal to the integral into the bracket of minus R all over P minus 3C all over T to the power of 4 into the P. This is what we are going to have. So we are going to be integrating this equation, mind you, from 1 to 2. We are going to be integrating this equation. So if we do this, at the left hand side here, the integral of 1 to 2 of the S is nothing but S2 minus S1. The integral of 1 to 2 of the s is nothing but s2 minus s1. So here we are going to be taking minus r minus 3c all over t to the power of 4 out of this integral sign. If we do that, we are going to have minus r minus 3c, that is minus r minus 3c. We are going to have, so here we are going to be integrating this. So before we integrate this, let's take minus 3c all over t to the power of 4 out of this integral sign. If we do that, we are going to have minus 3c all over t to the power of 4 minus 3c all over t to the power of 4 into the integral from 1 to 2 of minus r all over p. Minus r all over p, we have the p. So this is what we're going to have. So next, we are going to be, let's take r out of this integral sign. If we take r out of this, integral sign with the minus sign, we are going to be having minus 3c all over t to the power of 4 will remain. We are going to have minus r multiplying the integral of 1 to 2 minus 1 all over p. So we are going to have 1 all over p because we have taken minus r out. That is we are left with 1 all over p dp. So this is what we have. Now if we integrate further, this equation will become minus 3c all over t to the power of 4 minus r, where this equation will now become the bracket of in p from 1 to 2. This is what we have, dp. So this is what we have. So next, we are going to be simplifying this equation further. It will be equal to minus 3c all over t to the power of 4 minus r. By integrating this, we have in p from 1 to 2. If we put our limit, we'll be left with nothing but in p2 all over p1. So next, if we simplify the equation further, this equation is nothing but s2 minus s1, which is equal to, we have minus 3c, so we can start with minus r in to the bracket of p2 all over p1. This becomes minus r, the natural log of p2 all over p1 minus 3c all over t to the power of 4. So we can refer to this expression as an expression for entropy during an isothermal process, given the above equation of state. So this is what we have. Thank you for watching.